I'm going to talk about bounding negative energy density with quantum information, causality, and a little bit of chaos. So this is sort of, I'm sort of fleshing out some connections to the chaos bound, and so I'll try to do that in this talk a little bit. Okay, so as Aaron nicely told us, negative energy density is certainly allowed in quantum field theory. The total energy should probably be positive, but locally you can have small fluctuations where the energy density is negative. There's natural questions though. How negative can it be? Why do we care? Why is it bad that there's negative energy? And this is sort of interesting. The first reason is that if you take that quantum field theory, couple it to gravity, then you can do weird things like build time machines and so forth. And the second answer, which I'm going to talk about today, is that in quantum field theory, directly, if you have these negative energy density, then you violate things like microcausality, and you also violate sort of basic principles of quantum information. Okay, so and the context for all of this will be the quantum null energy condition, which again Aaron introduced. So this is a generalization of the classical null energy condition, which is the condition on the stress tensor. If I take the null components of the stress tensor in classical field theories, you always find things that are squared, so they're positive, sort of trivially. But in quantum mechanics, because of you have to normal order this operator, you have to make some subtractions. This operator is no longer necessarily a positive operator. In fact, it's not. However, recently there was a conjecture which bounds the null components of the stress tensor in terms of some somewhat non-local quantity on the right-hand side, which is related to the entanglement entropy. And so the setup is we have some entanglement, some region, and we're thinking about some general state, some very general state in the quantum field theory. We have that region, and we're thinking about entanglement between that region and outside of that region. And then, given that region, you can always, in relativistic quantum field theory, you can sort of shoot out light rays and make some light sheet. And then you think about deforming that light sheet sort of locally here and a little bump here, and you take the second derivative of the entanglement entropy with respect to that little bump, and that's meant to be the bound on TUU. Okay. And it was conjectured and then proven for free field theory and supernormalizable field theories. Okay, and so the natural question is there a general proof of the quantum null energy condition to more interacting theories? And that's what I'll try to present today. And the interesting thing is, to me, is that it sort of links many different ideas that people have thrown out to study mostly actually the problem of the emergence of gravity from space-time from quantum field theory in ADS-CFT. And then there's also chaos, and this talk will be a little bit chaotic, a lot of chaotic ideas, so that's maybe the most direct connection to chaos. Okay. Okay, so some things to keep in mind. QNEC is a conjectured property of quantum field theory. It's nothing to do with gravity, it's just a property of quantum field theory. We're going to work in flat space, although likely the methods can be extended to curved space. And we'll work with a general quantum field theory with an interacting UV fixed point in dimensions bigger than 2. And we're going to start by talking about the average null energy condition, which is a weaker energy condition. Okay, so there's two recent proofs of the ANEC, as Tom already mentioned. And the ANEC is a statement about an operator which is an integral of the stress tensor. So you take the null components of the stress tensor and you integrate it along the same null direction from minus infinity to infinity, let's say just in flat space, and then that operator should be positive, should be a positive operator. And if I just sort of integrate over, so there's always a sort of transverse direction to the null direction that we're considering, and if I just integrate over that transverse direction, I just get the null momentum operator, and that's sort of trivially positive. But this is sort of a local version of that, okay? And people were talking about the ANEC for a long time, have been talking about the ANEC for a long time, and that's because it's sort of predicted from general relativity because if you impose it when you couple the quantum field theory to gravity, then you can rule out various things like traversable wormholes. But it's also non-trivial in flat space. It's a non-trivial statement in flat space. For a CFT, it gives constraints on the three-point functions in the CFT. And in 4 dimensions, the three-point functions are related to, of the stress tensor in particular, related to the A and C trace anomaly coefficients. And as Diego and Juan showed, this gives interesting constraints. Okay, so the first method relates to interesting facts about modular Hamiltonians. So what's a modular Hamiltonian? Well, the standard setup for entanglement entropy, we have some Hilbert space, and let's just assume tensor factorization for now. And then we compute a reduced density matrix, and then we define an operator just by taking the log of that density matrix. And that's all a modular Hamiltonian is. It's the log of the reduced density matrix. However, this is sort of not well behaved. This operator in a continuum quantum field theory, it has UV divergences associated to it. And a better quantity is this full modular Hamiltonian where you take the modular Hamiltonian of the region A and you subtract the one for the barred region, for the opposite region. And so local divergence sort of cancel between these two terms. And these modular Hamiltonians have a nice positivity property, which is this positivity under inclusion. If I take a region which is smaller than A, B, so B is contained within A, then the difference in the full modular Hamiltonians is a positive operator. Okay? And this is proven using monotonicity of relative entropy. Okay, so now in a relativistic quantum field theory, we should not just talk about sort of spatial regions, we should talk about causal completions of those spatial regions. So we talk about sort of causal diamonds and causal wedges. This inclusion, this B contained in A, happens at the level of the causal domain. And so we can consider some interesting situations like this. So we'll take, our setup will be, well, in general, this statement about modular Hamiltonians is true for any state, but let's take the vacuum state for simplicity. And we take our original region A just to be a Rindler cut, so we take half of all space in the quantum field theory. And then we get the wedge-like region, which is called the Rindler wedge. And then we consider B to be a small deformation of that. So what I mean by that, a small null deformation. So we deform this in this U direction. And then we define B in this here. But this deformation depends on the transverse direction. So there's a transverse direction, so you can deform it sort of arbitrarily as a function of Y. And then what we did is we computed this difference perturbatively. We did some perturbation theory for these modular Hamiltonians, and we found the difference was related to an integral of this ANEC operator. And so then using the positivity property of this, you prove that is positive. And this was just a perturbative result for us, so we weren't sure whether there were corrections to this somehow in this perturbative expansion, taking delta x to be small, but this was recently proven to be an exact result. Okay. The second method uses causality of proving the ANEC. So that the microcausality, the statement that two operators that are space-like separated should commute, and this is a statement that's true in any state. So you can consider the following state. So we'll take the states to be psi, and let's just think about a state where I act on the vacuum with an operator which is inserted at a small imaginary time. Okay, so here's a picture of that. So here is my imaginary time. My Euclidean time is in this direction. My path integral sort of prepares a state which is now excited on this slice here. And then on this slice, using this state, I'm going to compute the commutator of two operators, which are space-like separated. So they're going to be blue and red here. But we're going to put them really close to being not space-like separated in this light cone limit. So we're going to send the V parameter of these operators to be small over here. And then the answer that you get, this commutator is then related to a 4-point function. And so, this 4-point function has been studied to death recently. Okay, so in particular, you can calculate in this light cone limit, the leading terms in this correlator, in this 4-point function. And this is what, sorry. I don't have the reference. This is what these people did. And so, if I bring two operators close together in a CFT, then I should be able to replace those operators by sum over local operators with OPE coefficients. The dominant operator is the one with the lowest dimension. However, in this light cone limit, it's a bit more subtle. You can now replace it with an operator which is integrated over this null direction. And the dominant operator is the one with the lowest twist. And so the operator with the lowest twist in many situations is just TUU. And so what you find for this correlator is, well, there's a contribution when you exchange the unit operator. You get, if you normalize it correctly, you get a 1, and then you get a correction, and the correction is just determined by this ANEC operator in that state psi, okay, evaluated in that state psi. And then there's some sort of kinematic factors that are out the front. The kinematic factors are just designed to be small in this limit, so v goes to 0. And then I've pulled out this factor which looks like e to the s times some number. And so this should remind you of the chaos-bound story of Maldacena, Schenker, Stanford, where they studied an out-of-time order thermal correlator, and they found that they found that thermal correlator had the following behavior. It looked like 1 minus a correction which was growing exponentially in time, and the coefficient of that they decided looked like a Lyapunov exponent. But in this situation, what is the time s? So s is playing the role of time. Well, here we're thinking of s, time as being a boost parameter. Okay, so it's well known that the vacuum state of a CFT or a quantum field theory looks like an entangled state between A and A bar, which then you can think of as a thermofield double state. Okay, and so this is so basically time evolution. So right, and then the reduced density matrix is then just given by e to the minus 2 pi HA, where this is the boost operator. Okay, so the boost operator is playing the role of the Hamiltonian, and so time evolution is just given by boosts. And so now we define this correlator where we have these state operator insertions and the two operators here, which are boosted by an amount s. And we boost them both, one in this direction by s and one in this direction by s. And so we reinterpret this 4-point, this vacuum correlation function as a thermal correlation function in Rindler space. And so you can rewrite it now in Rindler space. The other thing in Euclidean, the Rindler time evolution in Euclidean is then just rotations. And so I can reinterpret this correlation function as just a out-of-time order correlation function with some particular Schwinger-Keldysh contour with two time folds, where I have the two state operator insertions, and then I have my red and blue operators over here. They both move forward in time because boost, forward in time means boosting in this direction over here and this direction over here. Okay. And then from this, you can also extract the commutator. So this is what gives you this out-of-time order correlator. Sorry, the square of the commutator, which is the thing that's related to chaos. Okay, so then they showed that this function had certain properties, and we're going to use those properties here. And so the properties are that, well, it's an analytic function in the strip, the thermal strip of size beta over 2. It's computable in some limit, and it's bounded on the top and the bottom of the strips by 1. So the magnitude is bounded by 1 over here. And so it turns out that if you have a function like this, then you can use those properties to bound, to make statements about the parameters in this function here. In particular, you find this chaos bound that the Lyapunov exponent shouldn't be bigger than 2 pi over beta, and the coefficient in front of it should be positive. Okay. So there's two constraints. Here, the answer that Tom found is that the Lyapunov exponent exactly saturates this chaos bound. And so the only non-trivial thing you get is that the coefficient in front should be positive. And of course, the coefficient in front is just the ANEC. Okay, So this is their proof of the ANEC. So one important thing to say is that this calculation didn't need any large n limit. The small parameter is determined by the kinematics. And in particular, all interacting theories like this have the same Lyapunov exponent. So this is not a very discriminating version of chaos. You might not even call it chaos. Anyway. However, you can still give a story for what is chaotic about this situation. And basically what's happening is this state operator insertion is disrupting the local correlations, the entanglement that exists between A and A bar, that exists in the vacuum. And then when you boost, with the Rindler Hamiltonian, these two operators, this disruption becomes amplified, and this correlator decays. Okay, so if I didn't have these state operator insertions, then this operator would be boost invariant, and boosting wouldn't do anything. But with the state operator insertions, then this correlator decays because of this chaotic. Yes. Mm-hmm. Yeah, so this is for interacting theories. Yeah. But once you assume that, they all have the same exponent. Mm-hmm. Okay, so there's these two proofs of the ANEC. So how are they related? I don't know, actually. But what we're going to do is we're just going to put them together. Okay. And so let's go back to the original situation where we proved the ANEC, where we had this sort of inclusion property. So we had these two regions, and they were included in each other. Now, if I sort of ask what does that mean about the complement of the region A, it means that these two regions, the domain of dependence of the A bar region, is actually causally disconnected from this wedge region. So this statement becomes this statement in terms of the complement. And so now I can ask, can I communicate from this region to this region? In particular, microcausality, because they're space-like separated, should tell me that any operator I can create in these two regions has to commute. Okay? Any two operators, MB and MA, has to commute. Now, if I just use local operators, I won't get anything more than the ANEC. So I have to do something pretty non-trivial. And the thing that we're going to do is we're going to use modular flow. And so the idea is, instead of boosting with the Rindler Hamiltonian, which is what we did in this, in the original ANEC story, we're going to boost with the reduced density matrix of the excited state. Okay? So we take the reduced density matrix of the excited state, we take the log, that defines some Hamiltonian, and then we evolve with that Hamiltonian. Okay. And when we do this, we're probing negative energy that exists between this region here. Okay. Now, with this, then we do the same thing. We construct some chaos function, which is a correlator in the excited state of these two modular flow operators. Now, one thing to note is if I had taken the two regions to be, if I had taken B to be, this wedge region, so basically A, and this is A bar, then these two, then this function would be independent of S. And that's because modular flow, this state is essentially boost invariant under modular flow for this defining state. So that means this function would have been independent of S. So now what we have to do is to get something non-trivial is we have to split them. And we're going to split them by this amount delta U in this direction. Of course, once we've, this is all well and good. And this function you can actually show has the same properties as the chaos-bound function. However, it's a challenge to compute it because these new operators are very non-local and messy. However, we managed to make some progress in this same light cone limit that was used to prove the ANEC. And then, we can actually calculate this function, and we found, this sort of this one from the unit operator exchange plus a small correction, and this small correction is some more local version of the integrated stress tensor. In particular, now we integrate the stress tensor in this gap between here and here, and then we include derivatives of the entanglement entropy at the endpoints. So you can see that as I take the gap to be very small, what I get is just the stress tensor at that point and the second derivative of the entanglement entropy. So this is going to give the positivity of this quantity is then equivalent to the QNEC. Okay, so we computed this using a defect OPE, using the replica trick. And basically the most important thing about this equation is the 1 here. And the 1 is the statement that evolving with the modular Hamiltonian of the excited state for operators that are light-like separated from the defect looks very much like boosting that operator. So it looks like modular evolution for the non-excited state, which is then just a boost. Okay, so causality, etc., becomes a statement about analyticity of this function in the S-plane. And this you can actually show just generally using general statements from Tomita Takesaki theory and some generalizations of Borch's to this sort of double modular flow situation. So you have the same analyticity in the strip. Actually, the analyticity is extended. It's now 2 pi rather than just pi. But we can still bound this function along here using Cauchy-Schwarz argument. And again, you can use a contour deformation argument to write Q as an integral over these lines here and then prove that it's positive, which is the same idea as the chaos bound. Okay, let me give it some intuition for what's going on here. So this, actually, if we just go back to this modular flow correlator, but make everything vacuum, okay? So modular flow of an operator in vacuum is just a boost of that operator. So we just get 2 boosts. But the boosts are slightly shifted because one is boosting with respect to this wedge and the other is boosting with respect to this wedge. And if we combine these 2, what we get is just a small translation. Okay, so 2 modular flows with respect to 2 sort of deformed regions just gives you a small translation. And in particular, as I take S to be large, which is the region we're interested in, this just becomes, this deformation just becomes, this null deformation just becomes a null deformation of this length here. So it doesn't do much. There's nothing growing with S. But then, in this excited state, we're again disrupting the local correlations that exist in the vacuum state in such a way that these boosts are sort of effectively deformed a little bit, and they mismatch. And that mismatch then gets amplified. And so these operators just sort of get shifted over here. In particular, if the QNEC was violated, this operator would get boosted over here, and then you would clearly violate causality. Okay, I should have said before that this statement about the vacuum modular flow is actually related to the proof that these authors gave of the form of the full modular Hamiltonian for the deformed null regions. In particular, they showed that it satisfies some algebra, which is called the algebra of half-sided modular inclusions. And it's exactly that algebra that allows you to relate this vacuum modular flow correlator to just this null deformation here. So the excited state does not satisfy the properties that go into this half-sided modular inclusions. And so in some sense, the QNEC is some measure of how, how much this algebra is violated. All right. Okay, so let me just finish now. What's next? Well, I should mention the elephant in the room. The QNEC that we proved is actually an integrated version of the QNEC. The QNEC is, in general, is a statement about a second variation of the entanglement entropy, and those variations don't have to be coincident. When they're coincident, you get the stress tensor term. When they're not coincident, you get just strong subadditivity, which we know is true. So what we proved actually is an integrated version, which both contains the contact piece, which some people might call the QNEC. Let me call it the contact QNEC, and strong subadditivity. Recently, there's been hints that the actual contact QNEC is saturated, so there's no bound there. And if that's the case, or if you can actually prove that, then what we've given here is just a fancy proof of strong subadditivity, because our quantity contains strong subadditivity in it. One interesting puzzle, though, that I do not fully understand is that this saturation of the QNEC is actually just not true. In free quantum field theories, you can just compute it, and it's not zero. And the natural question is, how is it consistent when you add interactions? And so hopefully there'll be more on this soon, and hopefully we can strong-arm one of the students, maybe the Berkeley students, to give a talk about this in the Gong section next week. Okay, thank you.
Before turning on to the questions, let me remember that today we have the dinner for the speakers at the workshop and people that have been invited. For the others, the bus drivers say that they wait until 6:15. So we have according to my watch, we have 12 minutes, okay? So please.
So no questions.
Questions? Quick questions. Yes.
So when you say at the first bullet point you prove the transverse integrated QNEC, you can't just take the wedges to be different by a sort of wiggly slice to get arbitrarily close?
Oh yeah, we've also proved the contact QNEC, but we haven't proved saturation of the contact QNEC.
Okay, just wanted to.
It's not contained in that, yeah. Yeah.
Are you always considering modular flows associated with half spaces?
No.
So then are you always considering operators near the null surface of the...
Yes.
So this out-of-time autocorrelator with a parameter S,
Yes.
the chaotic behavior only occurs when your operator is close to the...
Well, we only have to consider two operators. We're actually working in a very general state. You can think of the state as being created by another operator insertion, but it's the two probe operators that have to be null separated.
Those operators need to be near the null surface.
No, they don't. They can be far, yeah. They can do whatever they want.
So then how come your modular evolution is approximated by a boost?
This comes from this defect OPE thing that I didn't go into. But basically, you use an OPE argument, which is similar to the ANEC OPE argument, except you replace things with operators that live on the defect in the replica trick. And so this you only require the probe operators to come close to the defect. It doesn't matter what else is happening with the defect.
Okay.
Any other question?
So this modular evolution that you do gives some particular non-local operator on the region, but the bulk picture sort of suggests that every sufficiently non-local operator would be dominated by the QNEC term in the null limit, just because as long as you smear something over the whole entanglement wedge, this is sort of the most singular term. Do you think that's the case? Or does that sound reasonable from your methods? That
I haven't had much sleep, so I'm not really sure. I'm not sure exactly what you're asking. I'm not following.
We could phrase your argument as causality of some non-local operator that came from this modular evolution.
Yes.
But the bulk picture suggests that every non-local operator would give the QNEC operator in the light cone limit.
That's not clear to me.
Just
Why?
because the bulk that's how the bulk regions come close together is by that little term that gives the QNEC operator.
You mean near the boundary?
Yeah.
I mean, why isn't there going to be contributions deep in the bulk, actually?
Won't they be closest near the boundary?
Okay, sure. Okay. Yeah. Okay. This sounds sort of consistent, though, actually, right? Is that what you're trying to say?
I guess I was wondering if it was obvious or do you think it's true? But
I haven't thought about it. Yeah.
Any other questions? Okay, let's thank Tom again.